The theme so far in this lesson has been how do we find patterns in stars and how do we use those patterns to then find more properties about those stars? In this video, I want to add one more aspect to that general idea. So far, we've been looking at how stars land on a chart, an HR diagram, and how we can use the trends that show up in that diagram to tell us more about the star. Today, we're going to look in this video about how can we use the colors of that star to figure out what the star is made out of. And turns out it has a lot to do with chemistry and the physics of the atom itself. So you may know that white light, if it's passed through a prism, so like white light from our sun passing through a prism, um, different colors of the light will bend differently, which give you a rainbow. That's ultimately just generally how a rainbow works, but instead of this nice acrylic prism, the sunlight is just going through little droplets of water, refracting the light into the rainbow color, just in another way. Now, that continuous spectrum doesn't tell the full story of what we're going to be getting into. Instead, um, something called an emission spectrum shows up when you have one particular element that you are exciting. So if you've ever seen like a neon light is exciting the element neon inside those tubes. Now, when that happens, it is going to start to glow. And from the looks of it, it looks like it's just made of a certain color. And sometimes it looks white. It looks like just a glowing light bulb. But if you were to put that through a prism, you're not going to get that same full rainbow that you did with the sunlight. Instead, you're going to get these weird discrete lines. And these lines show up at exact measurable wavelengths. So here, if we have hydrogen going through, we're going to see a spectrum, these little lines showing up, one violet, a blue green, and a red. This is always going to happen if you're using hydrogen. And each element has its own kind of unique signature in terms of its emission spectrum. That hydrogen looks like this top one. Sodium looks like the one shown here, then helium, then neon, then mercury. And you might already kind of get this analogy that you might already be thinking of it, but we can use these spectra to identify elements in the same way that you could use like a fingerprint to identify a suspect. That hydrogen makes this shape. So if we look up at a star and run it through a prism and see that shape, we know that there's hydrogen in that star. Likewise with sodium, helium, neon, mercury, and so on. If instead of exciting that gas, you have a hot source that's emitting a continuous spectrum, but it is then going through that gas, the gas will absorb some of that light. And it turns out that it will absorb the energy at those exact same wavelengths. So instead of seeing lines of light, you see a full spectrum with lines of light that are missing. And the emission spectrum and absorption spectrum are just like photonegatives of each other, that there's a line for every gap in the absorption spectrum. Now, the physics for why this happens at these weird discrete lines is something for another lecture, but basically the idea is that electrons can only exist at certain energy levels. You might remember that from chemistry. And if an electron is excited, it just jumps up different energy levels. When it falls back down from a higher energy level to a lower energy level, it emits its extra energy out as radiation. And that radiation being, in this case, in the visible part of the spectrum. And there are only so many different variables that could happen. You could go from the second energy level to the first, or the third to the first, or the fourth to the first. And every one of those will emit a different wavelength because it's a different total amount of energy. And each element has different gaps based on how big the atom is, how far away the energy levels are, or the different amounts of energy each energy level represents. So those discrete levels give us these emission spectrum and absorption spectrum. And if we look at a star, we're going to see something kind of this nature. That we see that if we look at a star, we see mostly a continuous spectrum, but there are gaps. There are some dark spots within that spectrum. Um, is this an example of an emission spectra or an absorption spectra based on our definition on the last slide? An emission spectra would be if it was nothing, but then just discrete lines of light. In this case, it's mostly light with discrete lines that are not there. So that is an absorption spectra. That means that these elements are absorbing part of that light before it makes it to the Earth. And we can actually use this uh, to help us identify what elements are present within a star. Here, if we look at this simulation, we can see kind of what this process looks like. Here, I'm pointing at different stars, running their light through a spectrum or through a prism, and getting a different star spectrum out. So say I started this star here, and I want to know what is this star made out of. Over here, I have the spectra of different known elements. Um, and basically, I need to figure out, okay, which fingerprints line up here. If I take a hydrogen and I pull it over here, we can see that there seems to be a really strong relationship between this star spectrum and hydrogen. So that's pretty good evidence that this star has a lot of hydrogen inside it. Instead, if I look at helium, if I pull it over, I can see that really the lines that weren't covered by hydrogen are covered by helium. So this first star is basically made out of helium and hydrogen, some combination of those two. So it could be a star very much like our sun, something that's undergoing nuclear fusion, fusing hydrogen into helium. If instead I look over here, I believe this is star number 2, notice that this spectrum looks very, very different. I see that there's a lot of these thick lines. So I'm going to run it across iron. See, does iron line up? It looks like there's some strong evidence that iron is part of that star. So it must be a really, really large, powerful star to be fusing iron in its core. If I look at calcium, I can see that there are certainly some spectral lines that match up with calcium. And then let's see, magnesium also lines up as well. So from this, I can see, and I could do this for any of these other stars as well. And I'll post the link if you want to try this out on your own. It's kind of a cool exercise to see, can you use these element fingerprints and the star spectrum to figure out what elements are in that particular star.